we are going to open also the, Jacobu, can you switch off can you mute your micro? Otherwise I have a sort of feedback, but you're totally welcome to use it if you have questions or other things, okay? So we are going to enter inside okay, good morning, Maria Aurora. So we are complete because Tarek maybe will come later. So the purpose of today is to apply some concepts that we mentioned during the course, but applied to one of the, how to say, applications of seismology. It could be considered applied seismology, and part of it will be covered also by Stefano Parolai, starting from the next week, but some of them are actually theoretical thoughts. And so we're going to look inside the basics of a hazard map, of the concepts that are rounding to build it, and some, how to say, thoughts about it. By the way, I'd been writing to Patrizia this morning, and she offered me a couple of dates. Very probably the exam will be on 26th of February. Should be Friday in the afternoon. That's due to the fact that the lecture room, the Stasi room, should be free on Friday 26th. So you will have the 2 weeks that are the standard to prepare your exam. By the way, let me tell you, we are going, during the oral exam, to discuss the concepts that we touched and discussed here. Again, if I'm going to ask you the representation theorem, you can start covering the blackboard with formulas, but what I prefer is formulas are nice, but logic. So understanding. So if you are going to mix two indexes, that's natural due to the many indexes that are appearing in many expressions, that's fine. What I really care is the logic, the thoughts, the concepts. And just a few like source spectrum, magnitude saturation Y, what about MW, something like that. What does it mean, represent a source, Y double couple. So what we discussed together, okay? So I will send to you a confirmation after the confirmation from Patrizia, but she told me that Friday 26, the room in the afternoon is available. So that's maybe the best possibility, okay?
Okay, so are we going to join you in the room or we'll connect here?
I don't know. I don't know. Probably you will. I don't know. We will see the engagement rules that will be valid on that day. Probably yes. Maybe once at a time. I don't know. But in principle, the place, the space-time will be Stasi room, afternoon of Friday 26. Maria Aurora, do you have a problem that you were raising your hand?
Exactly that question. If we would have to go to the ICTP or online.
Okay, look.
Or you need to, yes.
I don't know now, but for example, the exam rules at the university now, until now, the possibility was to make them by remote. We are starting from the next March. Also, exams in presence will be allowed. I don't know yet the ICTP rules. I don't know. I will tell you. But in your case, Maria Aurora, since you belong to PhD, we can also arrange a remote connection.
Okay.
Okay. We will see also, because you know that the rules between Italian regions are changing. Our colors can change. Today we are yellow, we can be orange. Maybe, I hope we will not be red. I don't know. No one knows until a few days before. But let's say that the date. Okay, Tarek, you did it.
Yeah, I did it. Yeah. So I'm in.
Are you alive?
Yes, I feel cold,
So
but I feel cold, but
yeah. So you're not in jail. Okay, that's good.
Yeah.
Good news. Okay, not yet. Okay. By the way, yes, today you are feeling, maybe for the first time, the cold bora, the real one.
Yeah.
So yesterday I was in Trieste, so it was starting. Today it's going to blow. Tomorrow it's going to blow, and then, well, that's winter. Okay, and waiting for the spring. Let's hope.
Yes.
By the way, okay. So Tarek, what I was saying until now, the important thing is that very probably the date of the exam will be the afternoon of Friday 26. So in 2 weeks, okay? As
Okay.
promised. We will discuss where. If in the Stasi room for you diploma guys, or I don't know, we will see. And last statement about this, okay, discussion about what we discussed here. You can fill blackboards with numbers and formulas, but that's fine, the correct ones. But please use concepts in your mind. That's what I'm carrying, okay? Okay, so let's try to close this course with a sort of application of some features that we discussed about source and propagation during this course. It's just a quick view about seismic hazard. You're going to discuss part of these issues in Stefano's course, starting from the next week. Some of them about the source, you will discuss them with Karim, because some of parts of this course are going to define the sources. But let's start. So a quick and final view about seismic hazard. Okay, let's start. Let me start sharing my screen. And let's go to the keynote here. Now, first about the definition. It's not trivial. But one thing is quite clear. Here I've been collecting some definitions that are available, starting from the, let's say, from the 90s. And this is coming from Leon Reiter, beautiful textbook, one of the first books devoted to hazard. It's dated, but okay, it's still containing the most important concepts here. Now, what is the difference in terminology between hazard and risk? Well, some nice visions can come from the etymology, because hazard in English, in Italian it's pericolosità, so connected to danger, and still not an easy etymology, but hazard is coming from ancient French, and actually it's coming from Arab, from the Arabic languages, because hazard could mean the dice, rolling the dice. While risk, it's coming from Latin, risicum, but still connected with danger, something that is threatening someone or goods or humans or things, whatever. But there is a calculation in that. So it's a sort of trying to get the measures about the danger. By the way, with these distinctions in mind, one of the first definitions was about the potential for dangers. Earthquake because of course we have a label seismic here. You can apply some concepts also to other natural hazards, like landslides or tsunamis, as we have seen, or meteor hazard or climate hazard, of course, with different declinations, with different space and time applications, or meteorological hazards, different timescales. But today, of course, we're going to discuss the seismic label. Okay, something that is related to earthquakes, like ground shaking, that's the most important one, or fault rupture, if you're very near to the fault, the slip, or some nonlinear effects. And when you're going to strong shaking some materials, okay, they are losing some elastic properties, and part of saturated soils may liquefy. So that's the natural hazard. Well, the risk in Leon's definition was a sort of an estimate. I don't fully agree with this definition, but it was one of the first, so of course it has been evolving in time. But it's a measure of probability of occurrence of these consequences. Okay, this is the first that I'm going to propose you. The second one is a little bit more updated. And again, we have here the physical phenomenon, like shaking, of course, associated with earthquake, that may cause. Of course, it depends where you are, in which environment you are, but the hazard is something that is connected with nature. And the risk is a probability that you have a social, so something that is hitting the human tissue, the anthropic tissue, and economic consequences. And you see there is a measure about the possible consequences. And maybe you have a value in mind. Another definition here, maybe it's the one that I prefer, but a physical effect in the first part associated with an earthquake, of course, like ground shaking, fault rupture, soil liquefaction, that may produce adverse effects. But of course, you can think, okay, if the same event is occurring on a desert zone, okay, it's going to happen, but maybe it's not producing some adverse effects. And actually the risk is the probability that the consequences, like damage, and that's the key word for today, can be measured, and maybe they will overcome a limit in some period of time. So this is the distinction, and to make things simple, we can use this very simple scheme here. But the risk in general, but today, of course, we are going to discuss the seismic label, is a sort of a convolution, because it's not an algebraic product. It's not a number times a number. Usually you adopt matrices or other things, but of something that can be called hazard, and that part will be nature decided. And what we can do is to assess it. Convolved with something that is related to what we can call vulnerability. For example, the quality of buildings, the typology of buildings, or the density of a population in some place. And that, of course, is in some way man-decided, and then it can be reduced. So if you want, we may have, to take the thing simple, we may have a place where we have a very large hazard, Japan, for example, and maybe we can lower a vulnerability. Like, for example, we can have very high quality buildings, a seismic code, that's an engineering aspect, but it's involving also with the seismological computation. But with the seismic code, you're trying to say, okay, you have to design buildings in this way, or what is called nowadays a performance-based design engineering. Okay, if this is happening, okay, the building, we accept that it's going to behave such that this is going to happen. That's a performance-based. But that is vulnerability. Inside vulnerability, you may have subdivisions. Like, for example, okay, you're considering building, you can have a fragility curve, or maybe you may have something that is more related to, for example, insurance companies. You may have exposure that is something that is related to a cost, okay? By the way, today we are going to discuss about hazard, but please remember that for risk, you have to couple it with other factors. And traditionally, the risk, is expressed in a probabilistic way, the risk. And in most of the cases, also the hazard. And this is what I'm going to discuss with you today. By the way, you may imagine that we have a set of events with an index. 1, none, 1,000, infinite, that may have possible adverse consequences. And to have a risk computation, you should try to associate some probabilities of their occurrence, or better, from my point of view, the probabilities of some effects on a zone that could be a national scale, so it could be a country, or it could be at a local scale, like a urban scale, or site-specific scale. And then for risk, you have to estimate what are the intolerable consequences. So this is the general picture that we can depict, trying to move and to apply some seismological concepts. Oh, pardon? Sorry, because I was closing. Is there something? I was hearing a beep from you, Maria.
Yes.
Everything is fine?
Yes, it was my connection that was unstable for a while.
Okay, let's start again. So let's take this relatively quick travel inside hazard. Let's start from the basics. And the basics are in time. For example, we can call this the oldest seismic hazard map. Well, you see a very nice picture that had been compiled by Robert Mollett long time ago. Instrumental seismology was not appearing there. Representation film was not there, but definitely many civilizations in the Mediterranean, in the Asian, in the original, how to say, the native Americas, there were the perfect knowledge of earthquakes and their consequences. But from a geographical point of view, this can be considered the first one, dated a long time ago. And you see some hotspots that Mollett was depicting here. But actually, this, of course, they were related to his huge activity of traveling and studying seismological phenomena. And according to the place that he visited, for example, when he was depicting this one, he was visiting Naples after an earthquake, or South Africa, as you see, or places that he was visiting. He was putting colors in places, that's Lisbon, of course, where he visited, and so he reported on this map. Okay, this is a beautiful piece of literature. Of course, it cannot be compared with modern maps, but it's a first trace of something that is putting some colors in dangerous zones, for example. From an historical point of view, the first, at least as a name, earthquake zoning map, actually it's not coming from what we could think, USA, for example, but actually it was coming from USSR, and it's dated back to a long time ago. And it was one of the first to be used, to be incorporated into a building code. That's unbelievable, because this is one of the purposes of a hazard zone. So try to define the zones with larger, smaller hazard, and so that we can tune or better design a seismic code. Okay, let's go to the modern and what we should discuss, hazard maps. Well, you have to know, but here, as usual, I'm cutting a long story short. But we can say that all the traditional hazard maps can come after a 1970 something, let's say 1968, from a dual possibility. And so what nowadays is called SHA, so seismic hazard assessment, at that time, and this is the collection of ideas made by Leon Reiter, one of the first publishers of a book about this topic here, actually traditional hazard maps can come from a dual way. And the dual way is called probabilistic and deterministic. Now, let me tell you that this distinction is still valid, but in some way, in the last 10 years, it has been overcome. Also, if most of the maps that you can see today are probabilistic, but we will not enter into this endless discussion, which one is better, but let's just see how to think about. Well, this is the traditional duality, probabilistic on the left, deterministic on the right. And it's made by modules. And the first module is the definition of sources. You can use point sources, line sources, area sources. Okay, we can think about a representation theorem. And of course, this different definition will lead to different models. Okay, good. And the first step is the definition relatively to a site. And you can consider a specific site, a set of sites inside a city or a country. Okay. So you can hear about the words about regional or local or site-specific hazard. By the way, the first step is common, and in my opinion, is still the most difficult one. The second step is the real dualism. Because now the determinist is saying, okay, given that site and given all the sources, I take the worst. Now, you could say, wow, why? Well, because I consider the worst, and if I design for the worst, I'm done. But one of the consequences of the deterministic was, okay, you are getting too large values, and to fulfill those requirements, it's too much. But maybe the worst earthquake is not occurring very often. So let's take into consideration the probability of occurrence of that event. And actually the probabilistic is saying, okay, according to the magnitude of all these events here, we can estimate their occurrence time. And this is the GR law that we discussed some minutes, but not some lectures ago. So with GR, if you remember, you have the logarithm of the number of an earthquake, you have a magnitude here, it's related to a given time interval. Let's imagine that it is per year. Okay, we take a magnitude here and we can estimate how many earthquakes with that magnitude can occur in 1 year. So the idea is to consider all of them, but weight them by their occurrence time. The determinists say, no, we take the worst. And the couple of parameters that are left here is the magnitude of the source and its distance to the site. And that's why the third step is common to both approaches, is the estimation of the ground motion at the site. And the third module, this one and this one, actually is common. And traditionally, it's done using what were called traditionally attenuation relationships. Nowadays, they are called GMPE. Let me try. Okay, some hazard here because this whiteboard can collapse because it's not its fault. It's my bad design here. GMPE, ground motion prediction equations. The concept is the same. The idea here is, okay, we have a magnitude, we have a parameter of the ground motion, here we have distance. Do you remember Richter? Okay, let's make a regression of all the data points that we have here, and we can estimate the amplitude. Here, we don't have just one, but we have all the possible events here with their different magnitudes, and we have different regression lines. Okay, done this, the deterministic approach has pretty much ended. Because, okay, I have a distance, I have one earthquake, one magnitude, I take this value here with a scatter, and then I tell you, okay, here the hazard is that value of the ground motion. Typically, it's the peak acceleration of a ground. So it's PGA. But nowadays, it's overcome. Peak ground acceleration. And that's the end for the deterministic. For probabilistic, now the results coming from all the sources are weighted in what is called an hazard curve. So the value of the acceleration depends on the magnitude that is related to an occurrence time. So you create what is called an hazard curve. Now let me continue for a couple of minutes and then we will make a pause. But let me tell you, first difference, all recurrence, on the other side, just one. Then there is another step. The output of a deterministic is, let's say, one value. Here, the probabilistic has two probabilistic approaches. One is this, occurrence time. The other one is that, okay, we are taking care about uncertainty. And the final output is given as a number. On the other side is given as an hazard curve. But wait a second, because let me tell you that after the 70s, especially starting from USA, the engineers preferred the probabilistic for two reasons. Well, essentially it's one, because you can scale the result according to time. Because of course, here you get one number. And if you're considering the worst earthquake and no occurrence or other probabilistic features, it's a value that is on average very high. Here, you can scale it down considering different return times. And this is what I want to discuss with you, because if you give a look to one of the most accepted maps at global scale, you got this. Now, this is dated because it's coming from 2000, but it's called G-shape in jargon. I don't know if the link is still active because they decided to remove it, but that's the global hazard map that has been refined in pretty much all the places in the world. But I want to, debunk it with you, because if you now see these beautiful colors, you could ask, okay, what do they colors? What these colors mean? Okay, and that's why I'm enlarging the legend here, and there you go. It's a peak ground acceleration in meters per second square with 10% probability of exceedance in 50 years. That is 475 year return period. So it's a measure of PGA with two possible definitions, with a return period of 475 or 10% probability of exceedance in 50 years. And then according to the value that you get, you can say very high hazard, higher, okay, that's a qualitative refrain. Okay, and the lecture could end here. But now let me ask you one thing. So let me go here. What's happening here? My God, I have to open it. Sorry. And let me go back. What is it? Stop sharing. Let me ask you. Well, let me ask you that you should ask why 4, 7, 5 years of return period? Well, now I want to discuss with you why. And I would like, my hope is that you will understand that this number, that is very, how to say, widespread in literature, where it's coming from and why in some cases it's a limitation. So my goal now is to debunk this. This is the most important message for today. Are you with me until now?
Yes.
Yes.
Okay. Now, let's use a very nice PDF that you can find on your Moodle websites, the two parallel ones. It's made by Netfield. It's a primer. So it has no meaning of being a complete document about probabilistic seismic hazard assessment, but it contains many important things that are the main message for today's lecture. So if you open the PDF, the last PDF that you can find on the Moodle website, you can find this. Share. So this is the PDF that is containing most of the standard topics that we discussed today. And it contains also the hint for the last homework that you should perform from today until the date of the exam. So I will trust you, or maybe I will ask you at the exam the answer. It's going to take, as all my suggested homeworks, 30 seconds, 2 years, it depends on you, or really 10 seconds. I will tell you what is the homework later. But now let's debunk PSHA using this 4 pages beautiful paper that is containing some important message. You see this acronym here. So PSHA, Probabilistic Seismic Hazard Analysis, a primer. Okay, we're going to discuss this in the second part of the lecture because it's containing one of the tools, maybe the most important tool, that is connecting the seismological world with seismic signals, with the displacement, velocity, accelerations, to the engineering community that is using, buildings, dams, skyscrapers, bridges, whatever. But what they do as a first and quite natural, quite reasonable approximation is to consider a building as a simple harmonic damped oscillator. So if you remember, we discussed it during the seismometry lecture, and we discussed the problem of the seismometer. And the forcing of a seismometer was the ground acceleration. Here, it's the same, but with a different perspective, because we don't want to measure the ground acceleration. That's the purpose of seismometer, accelerometer, velocimeter. But we want to understand the reaction of the oscillator to the ground forcing. Actually, what an engineer does is to consider a building and to approximate it into what is called SDOF, S-D-O-F. Let me write too many keywords today. Oh my gosh. Well, this whiteboard is a single degree of freedom system, can be approximated. I'm forcing it. It's going to vibrate. And I can call that a response spectrum. Single degree of freedom. It's a harmonic damped oscillator. Usually, you can find this 5% of damping. Now, since I'm working and teaching to engineers, every time I'm asking, okay, why 5%? What does it mean? Let me tell you, most of them, they do not know. Now, 5% of damping means that the damping inside the oscillator corresponds to 5% of the critical one. So if you go back, you should have discussed this during the wave physics course. If not, let me tell you that we discussed the Q factor during the +-1 lecture. And the Q is telling us the ratio, actually, between the forcing frequency, the natural frequency, pardon, and the damping in some way. No damping, it's infinite. Larger the damping is, smaller the Q is. Okay, when you discuss the damping of a system, you can define the critical damping. Critical damping usually is when, according to the parameterization of your harmonic oscillator, when omega 0, the natural frequency, is equal to 2b, and b is the viscosity, that's the critical one. 5% of it means that it's low damped. And they use this because on a sort of a rule of thumb, it corresponds to the average damping of a building. That's why you can find here the 5%. So the idea here is to force a single degree of freedom system with 5% damping, study its response, and computing what later we will call in a few slides response spectrum. By the way, let's go here. Seismic hazard source model. Now let's imagine to have a site or a set of sites. Let's imagine to have sources, a set of sources, 0, 1, 10, 1000. Each of them is characterized by magnitude, a distance to the site, and what is called a rate. So spatial distribution and a GR law, you see? Okay. Now something that can be read by you, and one hint will be here. But now what to do next is to use the estimate of the ground motion at the sites. How to do that? Well, attenuation relationship, or in modern days, they are called GMP. Here we have an example. Usually, they use the collected data of a parameter of the ground motion, typically PGA, but nowadays it's used, but it's preferred what we're going to call the spectral acceleration. Wait a couple of minutes. You take different magnitudes. You have a huge scatter, and now you should know why we have a huge scatter, because we have many factors that could decide the amplitude at a site at the same distance. They could be source effects, like, for example, radiation pattern. Propagation effects, Q, for example. Amplifications, wait a second. So we have a huge scatter. By the way, we take a regression, and usually it's a log norm regression. What does it mean? You take the logarithm of the value, and you assume here a normal distribution. So when you hear about log norm, there it is. Okay, and usually they parameterize the logarithm of the ground motion parameter according to magnitude and distance. So it's an evolution of what Charles Richter had been doing with his maps. Nowadays, GMP may contain many other parameters, like the type of faulting, if it is a strike slip, a deep slip, and other correction. But essentially, it's something that is relating magnitude, distance, and the value. Log normal, and that's important. Now, what is the probabilistic computation? Okay, now if you consider the PSHA at particular site, now you have one scenario. What does it mean? A given magnitude and a given distance. Okay, so the attenuation relationship, or you can call it nowadays GMPE, is telling us the distribution of the possible ground motion levels. And now we can ask, what is the probability of getting, with that magnitude, with that distance, a value larger than something? You're using the tables of the Gaussian curve. And so you can compute this. It's very analytic. It's very statistical. You have distance, you have magnitude, you have a line there, and you can compute the probability of being larger than something. You can do it. There are codes that are doing this. But what is important is coming here. Now, you take that, and for each magnitude, for each event, you multiply it by the rate of occurrence, the unknown one. So if you have a larger magnitude, if you take the GR, this R will be smaller than a magnitude 5. Now you take all the scenarios and you compute the summation. And then, and this is the last step, and this is one of the hints of your homework, you compute the probability of exceeding that value in some years. Of course, the probability is that the probability nothing is going to occur, 1 minus. This is referred as the hazard curve. Now, wait a second. Up to now, we are considering a generic set of events with a given magnitude, with a given distance, with a given attenuation relation. Then we weight it, and when we sum all of them, you take this number here, you call it capital R, you multiply by an amount of years. Please remember the 50 that appeared in the previous one. And then you get what you call an hazard curve at the site. Now, why this paper, this tiny exercise paper, is useful? Because it's making an example. And the example is a simple one, very simple. It's not realistic, maybe, but it's very simple. Let's imagine that we have at a site 2 scenarios. The first is magnitude 6, with a beautiful occurrence every 22. Then you have a magnitude 7.8, so it's larger, every 300 years. Both are strike slip and 10 kilometers. Now you go to the previous curves here. Imagine that you have here 7.8, and you begin your computations. Okay. Well, oh God, what is it? Sorry, I Okay. Now, you can compute R1, R2, so event number 1, event number 2. You multiply by the rate of each of them, 1/22, 1/300, and then you obtain these two curves here, R1, R2. What you can read here? Well, the ground motion parameter that is coming, and the rate of exceedance per year from your probabilistic computations. Each curve is coming from one event, and then for the cumulative probabilistic, you have to sum both. And then here you have this curve, this beautiful curve here that is the sum. Of course, R1 is getting lower values because the magnitude is lower. R2 is getting larger maximum values, but its rate of exceedance is lower because the magnitude is larger. So when you do the summation here, you combine them. And in principle, you forget about the single events and you get a cumulative curve. Now, this curve here is called the hazard curve. And what can you do here? Well, it depends. Because in my opinion, that's the best final output of a probabilistic. You leave it here, and that's the end. But actually, in practice, one additional step is done. Because that curve is Rn. Then you multiply by a t. And t, usually, it's considered to be 50 years. And here you get the same curve, but multiplied by 50. Okay, you can multiply by 1, by 75, by 2000, by whatever. Okay, the standard practice is to use 50 years. Let me go to the final step, and then we will make another 1-minute pause. So you see here, that's the hazard curve with a probability of exceedance, because now we can say, okay, given this Rn, what is the 10%, for example, probability of being overcome in 50 years? You have to pay attention, because in this picture here, the two labels for these two dotted and dashed lines should be reversed. That's a typo, if you want. By the way, here, let's imagine, because you see this is 0, 1. Now, let's compute the value of the ground motion that has a 10% of probability of being exceeded in 50 years. So you go to 0.1 here, you go here, and you read this value here. The answer is 0.6 g. But you could say, why 10%? Let's, for example, imagine to use 2%. You go here, here, and you get 1 g. So you have two different answers with the same hazard curve according to the probability of being overcome. Now, by standard methods, the one that is chosen is 10% in 50 years. So this is the reason that is explaining this. And now, the question for your homework. Why that choice, 10% in 50 years, corresponds to a return period of 475 years? And the question, as a consequence, is return period of what? Now, actually, the hint, everything is here.
Please, Prof. repeat the
No, wait. Let me conclude this. And actually, the question that I'm asking you is related about this formula here. Okay? So let me say it again, and then we will make a pause. The path that we have been building in this paper here is, okay, let's consider the scenarios. In this example, we have two. Let's consider their magnitude, and we have two. Let's consider their distance, and we have two with equal, it's 10 kilometers in this case. Let's multiply them for Rn. It's different because, of course, different magnitudes. Let's compute the summation. Then, and we can build the hazard curve. Then there is an additional step to consider this 50 years and to consider this 0.1. And from an hazard curve, you go to the values corresponding to that choice. Okay, now, pause. Is it clear what I'm asking? Tarek, you were asking something before.
Yeah, I was asking.
No, it was not.
One at a time. Tarek, you first.
No, I just wanted to tell you that it was not me, it was Tufir who wanted to ask.
Pardon, I'm missing you.
I told you it was not me that wanted to ask. It's
okay.
Tufir.
Sorry.
Yeah.
Sorry, because my screen was on the slide. Jacobo, maybe that was you.
Yes, please. I was asking the question again.
Okay.
Yeah.
The question is the following. If once you take the hazard curve and you decide a period of time that usually is 50 years, and then you decide a probability of being overcome that usually is 10%, as in that example, then this choice, that is the one that has been applied in the paper and that traditionally is applied to the hazard maps, this corresponds to a return period of 475. My question is, question number one, why? Question number two, and the return period of what? So, but actually my only question is, why? It takes 1 minute. Because the answer is here. The answer is here. But I want you to do the computation. And actually, the answer is, okay, I cannot resist. If you put here 50, if you put here 0.1, then you got an estimate of R. And I want you to think about that. So here, there is hidden the 475 years when you consider 50 years and, 50 years and 10%. If you want, the additional question is, okay, if I consider 2%, how much is the return period? I will tell you. It's 2,475 years. Now, what I want to tell you, and this is my principal message, and then we will go on, is that when you read on the maps this magic number here, don't think it is nature, because it's the result of 10% in 50 years. And you could ask, and why 10% in 50 years? Well, that was the standard after 1968, the seminal paper of Cornell, and he was an engineer, and he decided to use an amount of time that could be considered 50 years, the typical average life of a common building, of a normal building. Someone is saying that 50 years was also the time that was valid at that time for the release of licenses for nuclear power plants in the United States. And that's why they were interested in what was going to occur in 50 years. And why 10%? Well, okay, that was acceptable. Let me also tell you that nowadays, most of the maps are not using 10%, but 2%, with, of course, getting larger values. But my purpose here was showing to you the beautiful PSHA primer paper that is your homework. Actually, your homework is to understand that, is that the return period that you can hear actually is the result of a set of human choices. So there is nothing magic there, okay? That's my main message. So I repeated to you my question. Is it clear now?
Yeah, thank you. Yes.
Okay. Let's move to the second and final part of the lecture, because there are at least 3 themes that are overcoming the standard approach. The first, it's related to what I was calling response spectrum. And usually in presence, I would shake my power adapter there and forcing it. I did it with you when I was in front of the camera without making this. I can do with this, so I can force it. It's going to move, because actually PGA is a parameter, but it's not used that much in these days. You could ask, why PGA? Well, why acceleration? Because an engineer can couple acceleration with a mass, and you have a force. And you have a force that can be compared with one of the forces that are acting, the most important forces that are acting on buildings, gravity. And that's why in the engineering world, PGA was used traditionally, and that's why G is used as a unit measure, because it can be compared with the acceleration that is making the buildings stable, I hope, so to which they are designed. But actually, the measure that I'm using since the 70s, and nowadays it's in the standard codes, the engineers, it's no more only PGA, but also what we can call spectral acceleration or spectral velocity or spectral displacement. Let me tell you one thing. This topic here, I'm spending a whole course at the university. So I'm just making a very panoramic view about terminology things that maybe you're going to listen in the future. So we have seen this picture from the Nedfield paper. And let me tell you what is the idea. Let's imagine now that you have a set of buildings with different heights. You know from the theory of the pendulum that the period of the pendulum is 2 pi times the square root of the length over g. So longer the pendulum, higher the building is, longer the period of vibration will be. So you can imagine to have different buildings from the skyscraper to your house, and you have different pendula with different lengths, from very long to shorter, 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 and to 0 length. Then you imagine to force all of them with the same acceleration. Each of them has its response in time, so that's the response. You see these time histories here, and then you take the maximum as a value, and you plot that. So actually you have a plot that is made by period, and period means period of vibration, and an acceleration, and that acceleration is called spectral acceleration. So in that way, an engineer has the idea of the maximum acceleration that is forcing the building at its natural frequency. That is called spectral acceleration. You can do the same also, not measuring acceleration, but for example, measuring displacement. But remember that the forcing is still an acceleration. So instead of measuring the acceleration time series of this DOF, you measure the maximum displacement, and that is called spectral displacement. So message number one, PGA is no more the only used parameter. More often, it's used spectral acceleration at different periods of vibration. Message number one. And let me couple this message with one of the last slides here immediately, because PGA as a single demand parameter has a strong limit. Like for example, in this case here. Here I'm showing to you two totally different acceleration time histories, totally different. One has been recorded, had been recorded in Italy, in central Italy, in 1971, and it was related to a very tiny earthquake. It caused some damage, but local damage. The other one is the famous Northridge earthquake, 6.7, 1994. And if you look, the maximum value of the acceleration time history is the same, pretty much the same, it's 0.8. But look at these signals, they have a totally different frequency content. So very high frequency, large vibration, but at very high frequency. Here you see this long period message here. This is much more dangerous, but same PGA. And another example here that is showing a record that I tragically love, because it's the one recorded in one of the horizontal components in downtown in Mexico City, in Distrito Federal on September 1985. And look at it, because I'm going to spend one slide about it, and compare these two. They have again the same PGA, a little bit less than 0.2. But look at the differences in duration and frequency content. So my main message, one of the first main messages here is, okay, that's nice, a beautiful seismic hazard map showing PGA. Let me tell you, it's not the end of the story, because there are some ground motion parameters that are much more related, in many cases, with damage than PGA. And going backward, let me show to you this. Because it's coming from, I started this course showing to you some of the pictures of the data, of the concepts arising from the Toku March 2011 earthquake. So we have seen the very long period, the GPS motion, long period, short period, the rupture, the acceleration, the tsunamis of that event. And I want to show you the record obtained for that event in a relatively small city, Tsukidate. That's the location. This is what has been collected. And if you look at these acceleration time histories, they are impressive because you have here signals with 3G of acceleration. That's huge. You can imagine stones thrown, because 3G means that it's 3 times the acceleration of gravity. But if you give a look to the response spectra of these signals here, what you get is the following. Response acceleration, now you know. What you see here is that most of the energy is concentrated at very low periods, very high frequency. You see how much high are the frequencies here. Actually, the peaks are huge, but at relatively short periods. The Japanese design code that was valid at the time was this, and it has been elaborated after the 95, if I remember correctly, Kobe earthquake that destroyed a city, totally destroyed, with thousands of victims there. But you see that here, the most attention is given to periods around 1 second and longer. So again, my message here is that, okay, you may have very large PGA, but if the energy is concentrated at very high frequencies, you can have some local damage, but actually it's not making to collapse buildings in most of the cases. And actually, these are some pictures that have been collected in Kuriara city, that is in the Tsukidate province, after the event. You see there is some damage here, but mainly concentrated in some non-structural, refer to the building, damage, as you can see here. Very high frequency, very large PGA, impressive, but pretty much no damage there. So message number one, PGA is not telling the whole story of the ground motion. Now let me go to the final messages, because one is related to source effects. Okay, you should remember also this picture here, because I've shown it during the seismometry lecture, and it's coming from the Michoacan event in 1985, recorded very near to the source. And I was showing it to you for two reasons. The first one is to distinguish between the different domains: acceleration, velocity, displacement. This was an example of a strong motion. Different units, different frequency content. So you see here, acceleration is, okay, 0.1 g, not that much, but very rich of high frequency. Velocity, this is containing some source effects here. And within the source effects, please notice that we have a static displacement. You can call it coseismic slip, you can call it near field. So if your building is located near the fault, that could be very important. Okay, that's not frequently the case, maybe some parts in California, maybe in some places for inland earthquakes in Japan, but definitely what is important from the source point of view is also directivity. Because directivity that we studied for the source spectrum actually can change a lot the signature of a ground motion. If you remember, stay in front, the rupture is coming to you, the signal can get shorter but larger, in the back can get longer and smaller. Well, after the Landers 1992 event, the first acceleration recordings near the fault, well, not the first maybe, but the most discussed recordings, here we are in California, here we have the rupture that had been evolving like that. That's the Joshua Tree and Lucerne Valley receivers. And you see here how the same source was giving totally different acceleration time histories. Forward directivity, backward directivity. And this is actually the displacement recorded there. Look at the fling. Why I'm saying fling? Because if these facts were known in the seismological community, and you know them because we discussed them, because we call them the near field in the Green's function and near source effect, and they had been studied by Stokes and Green and Benioff a long time ago. Nowadays, they are incorporated in the seismic codes, and they are called fling effect and directivity effect, as you can guess. I was hiding these slides here, but let me discover unofficially for you this, that is one of the first regression examples of that are taking care about directivity. So Tarek, this was one of your questions some lectures ago. And here there is a sort of an answer, because source effects can be very important there. But look at the distances. So when we are in a regime of distances that are comparable with the dimension of a fault, we are in the near fault regime. So directivity can be important there. And this is one of the most important topics in hazard today, how to incorporate them. And let me also show to you that standard regression laws, look at the data, most amount of data here, especially for large events, are starting from 10 kilometers to here. So here, at these distances, source effects can play very important roles, but we don't have a large amount of data. And that's why modeling using the theoretical approach that we discussed during this course could be important. So the last pose here, if you remember, Tarek, you had been asking, if I remember correctly,
yes.
the near fault condition. Okay, so maybe you have seen here an example of its importance, not only in the theory of a seismic source, but also in the definition of a seismic input. Because if you have a signal that is very large but very short, you're going to hit the building for a short time, but with large amplitudes. On the other side, if you're seeing the backward, okay, the building is going to be forced by lower amplitudes, but they are long-lasting. And it depends on the kind of a building. If it is made by concrete or masonry, which of the two inputs is the worst? Well, it depends also on the building. So I hope that I've shown to you an example of the importance of a near source effect in hazard.
Yes.
Is that okay?
Yes.
Okay. So let's go now to the final topic. So second message. In the standard seismic hazard, not only PGA is a limit, and nowadays we use SA, spectral acceleration, but some additional effects like source effects are incorporated. And one of the effects that is incorporated after 1985, and this is, let's say, the last discussion, was actually coming from the experience of a Michoacan 1985 event and the effects that it had on Mexico City. The F stands for Distrito Federal, that is the nickname, or some, let's say, the F is the name of Mexico City, of its district. Now, why it's important? Well, for this, because the source that released the seismic energy, pardon?
Am I the only one who don't see the slide?
Oh, sorry, I have to, thank you. Thank you. Here it is. Do you see it now?
Yes.
Yes.
Okay, so the important parameter here to look is this, 400 kilometers. Actually, when that event occurred, the Mexican seismological community that was very well developed, Sin Alumni is one of the most important seismologists at the time in the world, passed away a few years ago. He was traveling from Mexico City, he was working at UNAM, to Michoacan just to check the damage that was there. And actually, you have seen the recordings near the source, like, for example, this one. You've seen it before, with also some near source and near field effects. So you are waiting that after 400 kilometers, the effects are going to be zero. But, okay, the wave train here was getting lower and lower in amplitudes and less rich of high frequency, as we know from the Q lecture. Well, but actually, when the wave field approached Mexico City, it found the ancient lake sediments. Why the ancient lake? Well, this should come later, pardon. I'm reversing the presentation. Because the older Tenochtitlan was built in the middle of a lake before the Spanish conquistadors decided to take it. And I think they spent 10 years to take this city. But you see, in this beautiful old painting, you see the old Mexico City. It was not Mexico City, it was Tenochtitlan, with just few entrances here in the middle of a relatively deep lake. And you see it also here. Well, that zone nowadays is, let's say, here. It's very near, it's supposed to be very near to the central square of Mexico City, Zocalo. But you see, it's a tiny place in the middle of a mega city, modern mega city. But the point is that many parts of a modern mega city are built on sediments, ancient lake sediments. And due to the impedance contrast, one can say, and I'm going to use the whiteboard again here with some risk, that the wave field was arriving there low, very low amplitude and very poor of high frequencies, but it was very rich of periods around 1 second. Okay, and then there was the first resonance, because the impedance contrast between the ancient sediments there and the bedrock, since they are relatively deep, amplified, locally amplified, the amplitudes at the periods between 1 and 2 seconds. So there was a reprise of amplitude. Locally, it was not a violation of energy, of conservation of energy, of course, but the wave field was increasing in some periods. It's like the resonance of a pendulum, more complicated, of course. And so the signal that was arriving there, in some places where there are the old sediments, it was increasing in amplitude, not violating the conservation of energy. Here you see the old town, that's consolidated deposits. But here there are many places that are built on ancient lake. So look at the amplification in some places of the city. And they coupled with the natural period of very tall buildings that have been built during the 40s and 50s in Mexico City, relatively new, and their height caused their natural frequency to be around 2 and 3 seconds. So a chain of resonances make these effects here. That many tall buildings located in some special places in Mexico City, 400 kilometers from the event, they collapsed. And since I'm going pretty much to the reverse, I'm going to show to you now one of the final pictures, because this was the seismic code that was valid in Mexico before 19 September of 1985. And it was a very high standard, but it was missing, this is the response spectra, this is the natural period, it was missing this amplification here. Why? Because building the seismic code, creating the hazard maps, at that time they used the attenuation relationships coming from California. And in California, there are not in most of the places, very deep sediments. So the local amplification was not inside the GMPE or the attenuation relationships that they used. And so this is what nature provided at many buildings there. So As a second and final message, not only PGA, but I say, source effects should be incorporated, and site effects, well, it's, let's say, at least 20 years that they are incorporated. And please remember that the distance of Mexico City from the source was 400 kilometers. Look at the standard GMP. Usually they're stopping at 200 kilometers. So no one was waiting, nothing there, but many buildings collapsed. And it's not a precise account, but maybe a couple of 10 of thousands of people died in Mexico City for site effects. And very final message here is that in codes, usually, source and site effects are considered, but kept separated. But please, and so usually, the important issues in modern site response estimation, that's the acronym that is here, usually site effects are related to the impedance contrast of sediments over a bedrock. And the key parameter there that is used is surface shear wave velocity, VS. And so that's the important factor there. And that's why in many codes, now you see that to characterize the sites, V30 is used. It's a sort of an average of S-wave velocity in the first 30 meters. You can ask, why 30 meters? I will tell you, nature is not there because 30 meters is the average depth that you can reach in one day of making holes in the ground, of boreholes. So it's not a magic number, but the idea is to have a parameter that is telling us the potential amplification at a local site. Please do remember that, of course, this estimate is valid, but there are some local amplifications that are strongly affected by the shape and the depth of basins. And you may have basin edge induced waves. And you can have this coupling with subsurface focusing at very tiny scales. For example, you may have here the bedrock situation, another sedimentary environment, like for example, the one that is in LA, that is a thick sediments there, and you may have large amplifications due also to subsurface focusing at just few meters apart. So please remember that site effects can be very important in many things here. And so PGA, source effects, site effects, please remember that to define the average behavior of a site relative to all the other ones, according to all the possible sources, may be a very difficult topic, very difficult task. And that's why the final picture is coming from, well, it's 20 years old now, but it's still keeping its message here. It's coming from the beautiful computations that Kim Beck-Olsen performed for California there. And what he was doing was using the same 3D model of a sedimentary basin. We are in California here, so it's the Los Angeles Basin. And he was using different sources. So if site effect can be defined apart from the source, the local amplifications, the local hotspots should be the same given all the sources. But it's not the case, of course, because the interaction of a seismic wave field generated by a source, as we discussed, interacting with the 3D basins can be very different. And this is an example. For example, here he was using, the model with Northridge earthquake. Here, 2 rupture on the San Andreas fault. Here, other 6 scenarios. You see the fault here, a line, a point, an extended fault. My message here is, it's the same situation, but source effects combined with site effects can cause very different hotspots here. So from a physical point of view, from a theoretical seismology point of view, please do remember that source effects and site effects that are very important for hazard, they are usually treated as correction factors for one and the other, but in many cases where you have, for example, basins very near to sources, they are all together. So still a lot of work has to be done. And let me close with this final slide that it could be considered a sort of a summary of what we have seen together and also what you have seen in other courses and what you're going to see in other courses. Because we are running through many time and space scales. Space, we can consider the global seismology or country size seismology or urban size or specific site, so different space scales. And so global, rupture, whatever, and also time scales. For example, the time scales of the seismic cycle, also if it is not a cycle, or how to say, geodetical and geodynamic scales, or the decades of a GR law, or the seconds of a single rupture and propagation of the waves. So we may have different actions to deal with. And we have to put together geodynamics, geodesy, and seismology, of course, to take care about that. And for example, on this side, we may have to study strain rates, like for example, the one studied by GPS, to have deformation studies, and slip rates if we want to go on the single fault side. And we may have so different time and space actions. So for example, the most important one maybe is to have a seismic code in a country. The space scale is national and it has no time connected because it should be forever if it is a good code, of course, incorporating source and side effects. Or maybe you can go to, on a decade, on the 10 years, decades time scale, could be regional. You may have some local alerts coming from, for example, from geodesy and geodynamics. On the other side, we may have very short time scales, seconds, urban scales, and to give red alerts. We can do that, for example, for tsunami warning systems. There are some earthquake warning systems, and in Japan they are working at least to stop Shinkansen, to stop the elevators. But in Japan, in many cases, we have a sort of a time scale that could be up to minutes, as we have seen, okay, tens of minutes for tsunami. So this could be effective, but in many countries of the world, we don't have such a long time to act. So at urban scale and to go to short time scales, maybe this is still something that has to be worked on. Okay, so, okay. Let me stop sharing my screen here. So as I told you, well, today we are pretty much on time. Okay. It was a very quick view of some topics. Seismic hazard maps, the terminology that is used there. So please remember what is called the hazard curve, what is the next step to give a period, 50 years, probability, 10%, return period, your homework. Ground motion parameters as an output, traditionally PGA, but the most modern one is seismic, I'm sorry, I'm getting tired now. Spectral acceleration is the most important and different periods, response spectrum. And incorporation of source and site effects there. So it's one way to couple what we discuss in theoretical seismology, but also with some application with the social, political, engineering community for hazard. So, okay, my friends, that's the end of the course. On the Moodle website, you have all the PDF that we discussed together and also the additional material. Please take some time to solve the last homework. It's about, actually, it's just reading. Remember, the most important one was the one related to the reading of Ockel and Stein, piece of paper about the moment magnitude. I will ask you at the exam. And today's one is related to reading again the net field short paper and to use the 10% and 50 years to get the 475. It takes 1 minute. Okay, that's it. As soon as I get a confirmation from Patrizia, I will also send to you an email about the place and time about the exam. Okay?
Okay, Professor, yes.
Okay, so let me tell you. Good afternoon, good weekend, good everything, and see you soon. Well, not so soon,
Okay.
in a couple of weeks, okay?
Okay.
And we will see, yes? Okay, and I will send to you an email as soon as some rules will be defined, okay?
Okay.
Okay, goodbye,
Bye-bye.
and good everything.
Thank you.
The same for you.
Thank you.
Okay.
Bye.